What is the grammar for the following language over sigma is equal to a comma b? The language given as w says that number of a's of w mod 3 is equal to 0. So this language indicates that total number of a's present in the string must be multiple of 3. B's can be any number. We can accept minimum string epsilon. Actually in the options the lambda is nothing but it is an epsilon. That is, it is a null string. It is a representation of a null string. We can have different notations for epsilon. That is epsilon, cap, lambda. These are all the notations for the strings which are of length 0. So here we need to have a grammar for this. Anyway, it is a regular language. We can have the DFA. So we can have 3 states for this. Number of A's can be, we can have 3 states like this. S, A and B. Let us take these are 3 states. So minimum number of A's can be 0 because 0 is a multiple of 3. So starting state can be a final state, epsilon accepted. After without considering B's, if only A's are considered, for example, after epsilon you can have 3 A's, 6 A's, something like this. 3 A's, 6 A's like this. Okay, so that means we can have transition A to A, B to A. Again, B's can be any number. We can give a self loop over the B's. So that means this is the DFA for all strings of A's and B's where number of A's are multiple of 3. So when S is epsilon, so it generates S2 epsilon also, or lambda we can say. So when S2 AA, because this is the regular grammar equivalent to this AA, S2 BS. Similarly, A transitions are what? A transitions are A is giving A to B. So A to AB, A is giving BA or BA. So B gives AS or anyway S is epsilon, now we will give A also BB. So this is the equivalent grammar, because if there is a production, there is a transition from S to A with small a, then S to AA is the equivalent right linear grammar production, regular grammar production. If it is final, epsilon also will be coming. If it is not final, no epsilon will come. That means if it is A is final, for example, then you get S to AA or small a also, because A generates epsilon if it is final. So like this, if it is not a final, AA only will come. So according to that we convert it. So this grammar is equivalent to AA, BS or epsilon, because S is final, A to AB or BA and B to AS or BB. It generates all the strings with number of A's multiple of 3. Option C is the correct option here.
A graph is given and we have to find the weight of the minimal spanning tree using Prim's algorithm. Starting with vertex A. Here starting vertex is given as A. So according to the Prim's algorithm, we have to see the edges that are incident on vertex A and we have to select the edge with minimum cost and we have to add that edge to the spanning tree. So here on vertex A, 3 edges are incident. One with 5, cost 5, one with 4 and other with 3. So we have to select the edge with minimum cost and we have to add it to the spanning tree. So according to Prim's algorithm, we have to add the edge AD to the spanning tree. So in the spanning tree, now we have 2 vertices. Now we have to see the edges from the graph which are incident on those 2 edges, on those 2 vertices, and we have to select the edge with minimum cost. So on A we have 3 edges with cost 4, 5 and 3, and on D we have edges with cost 2 and 6. So among these 5 edges, the edge with minimum cost is DE. So we have to add the respective edge in the spanning tree. So we have added edge DE. Now, in the spanning tree, we have 3 vertices and we have to select the edge with minimum cost incident on those 3 edges from the original graph. So the next edge in the spanning tree would be EC. We have to add EC in the spanning tree. So like that we have to proceed until we get spanning tree. So the next edge would be CB. So we add CB to the spanning tree. Cost of CB is 2. And the next edge would be CF. So we add CF and the cost of CF is 4. The number of edges in the spanning tree would be n minus 1, where n is the number of vertices in the graph. So the resultant spanning tree would be this one. And the cost of the spanning tree is 3 plus 2 plus 1 plus 4 plus 2, which is equal to 12, which is option C.
We want the process P2 should go in critical section only after P1 has left its critical section. A and B are semaphores and the following code is used to implement the above scenario. So here there are two processes P1 and P2. We have to execute P1, we have to allow the process P1 to go into critical section with a statement at X and Y, both are the entry and exit sections. For P2, W is entry section, Z is the exit section, for example. So our requirement is we want to allow the P2 only after P1 has left. That means even if the CPU is in the hand of P2, we don't allow P2 to go into critical section unless P1 has entered into critical section and came out. So for that, so we have to use some semaphores A and B. Those two semaphores can be called through either wait operation or signal operation. So for example, if you use any semaphore A or B, for example, then that initial value must be 1. Then only P1 can freely go into critical section. The semaphore that would be used at W, that initial value should be 0. For example, if you take option A, X weight of B, for example, weight of B is used, at Y signal of A is used, and at W what is used, weight of A, and at Z signal of B. So these are the things used at X, Y, W and Z. So for example, if you take B value should be 1. Here A value is 0, B value 1. A value is 0, whenever you try with P2, P2 cannot go into critical section because it stops. Nothing will be done when the semaphore value is 0 in a wait operation. If it is other than 0, it will go into next statement. So B value is 1, it will go. After P1 has come out, it will give a signal so that A value will become 1, because initial value of A is taken as 0, no? So that will become 1, so that it allows the process P2 into critical section. After P2 has come out again, P1 can go. So this is option A. Option A is the correct option.